Welcome to Summarize Science. Have you ever watched smoke swirl or water churn and wondered if there's a predictable pattern to the chaos? For centuries, scientists have used the famous Navier-Stokes equations to describe the motion of fluids, but these equations hide deep and perplexing secrets. In fact, understanding them fully is one of the 7 Millennium Prize Problems, with a $1 million reward. While that grand prize is still unclaimed, a team of mathematicians has just made a groundbreaking discovery about a core aspect of these equations. They tackled a fundamental question: is fluid flow deterministic? In other words, if you could set up a fluid in the exact same way twice, would it always evolve into the exact same future? In a landmark paper, they proved that for a certain class of solutions, the answer is a resounding no. Their main theorem states that there can be infinitely many distinct solutions to the Navier-Stokes equations, all starting from the very same initial conditions. This means that from one single starting point, a fluid could theoretically evolve into an infinite number of different futures. So how did they prove something so profound? Instead of tackling the whole problem at once, they focused on a special type of flow called a self-similar solution. You can think of these as patterns that maintain their essential shape even as they shrink or grow over time. The key insight was to test the stability of this self-similar solution. They discovered what's called an unstable eigenpair, which is a sophisticated way of saying the solution is fundamentally unstable. It's like perfectly balancing a pencil on its tip. It's a valid position, but the slightest nudge will cause it to fall in a completely new and unpredictable way. Proving this instability required mind-bogglingly precise calculations, far beyond what any human could perform by hand. This is where the computer-assisted proof comes in. The researchers developed an innovative numerical framework and used computers to rigorously verify key steps, turning high-precision numerical evidence into a solid mathematical proof. The paper even provides visualizations of these concepts. Here you can see their primary solution, and in these other figures, you can see how adding a small perturbation dramatically changes the flow, creating new swirls and patterns. Each of these represents a different possible future for the fluid, all stemming from a nearly identical start. So let's recap the breakthrough. The researchers constructed a special solution to the 3D Navier-Stokes equations and proved it was unstable. This instability means that tiny, imperceptible differences can lead to wildly different outcomes, confirming the existence of infinitely many possible futures for a fluid, even when it starts from the same initial state. While this doesn't solve the full Millennium Problem, it is a monumental achievement. It establishes a fundamental non-uniqueness and unpredictability at the heart of our mathematical description of fluids. Furthermore, their powerful computer-assisted method provides a new toolkit for tackling some of the most difficult questions in mathematics and physics. Thanks for watching this episode of Summarize Science.